Bueno, buenos días a todos. Vamos a comenzar con la segunda parte ya del Congreso, en concreto con esta tercera plenaria, que en esta ocasión está patrocinada por el Grupo Arcamo. Tenéis ahí la documentación. Desde el comité organizador, cuando nos planteamos esta serie de conferencias plenarias, intentamos englobarlas todas dentro de lo que hemos llamado Fundamental Catalysis. Y además de contar con excelentes conferenciantes como el profesor Guido Busca y el profesor Javier Pérez Ramírez, nos hacía especial ilusión contar con la presencia de Beatriz Rolda Cuenya, que además también ha sido premio 2022 Polemes de Fundamental Catalysis por la Sociedad Norteamericana de Catálisis. Y para nosotros le queremos especialmente agradecer a ella que haya hecho un hueco en su agenda y haya podido estar aquí con todos nosotros compartiendo estos días. Beatriz es española, es de Oviedo, es física, además también ha hecho su postdoc en Ingeniería Química y después de pasar por diferentes centros como la Universidad de California y la Universidad Central de Florida y como catedrática de física de sólidos, ¿no? Desde 2017 es directora del Departamento de Ciencias de Interfaces del Instituto Friedhaber de la Sociedad Max Planck. También directora del Departamento de Química Inorgánica y profesora en 2 universidades en Berlín. No me voy a detener a explicar todo su currículum, ¿no? Todos sus artículos, patentes y muchos premios y reconocimientos, que son muchos, ¿no? Entre otros la medalla Faraday y el Rotem Medal, que además de tener los varios premios Nobel, solo hay 2 mujeres que en los últimos 70 años lo han conseguido y una de ellas la tenemos aquí. Entonces, para nosotros es un honor. Y lo que sí me gustaría comentar un poco es lo que yo creo que a todo el comité, y supongo que los que habéis compartido algún momentillo con ella, es que es una persona muy cercana, que se puede hablar con ella, es muy agradable, es muy simpática, es versátil, porque una persona que es física y trabaja en ingeniería química, además de inteligente, se adapta a cualquier medio. Y además es luchadora, es defensora de causas que considera justas, es una persona que ha demostrado tener un sacrificio, un esfuerzo para lograr todo lo que ha conseguido y además es generosa. Se ve que intenta ayudar siempre a todos los que están cerca, ¿no? Se cruzan en su camino para que intenten mejorar. Por lo tanto, además de tener una excelente científica, tenemos aquí a una brillante persona. Así que yo no me entretengo más porque seguro que la charla va a ser muy, muy divertida, muy entretenida y vamos a aprender mucho y con todos ustedes, Beatriz Rolda Cuenya.
Qué bien se está en casa. Con esa introducción, que es la mejor que me han dado en 25 años, ahora no sé cómo voy a hacer para estar a ese nivel, ¿eh? Muchas gracias por la invitación, a Luis, al comité organizador, a todos los estudiantes que están ahí asegurándose de que todo esto funcione, que sé que lleva mucho tiempo organizar una conferencia. Voy a darme charla en inglés porque llevo 25 años fuera de España y es más fácil para mí hablar en inglés en las charlas, pero después venir a preguntarme en español y venir a hablar conmigo. Como pensaba que a lo mejor no se conocía mi instituto de investigación o quizá la Sociedad Max Planck no es conocida, voy a introducirlo rápidamente y luego voy a empezar a hablar de ciencia. La Sociedad Max Planck tiene 85 institutos en Alemania. Tenemos 24.000 empleados científicos, también algunos de administración, y hemos tenido 30 premios Nobel en los últimos años, el de física y de química, y con mucho éxito últimamente. Para que os hagáis una idea, nos financia el gobierno alemán y tenemos 2,1 billones de presupuesto. Este es el campus del Instituto Fritz Haber Institute. Ahora os voy a dar unos detalles. Estamos en Berlín. Esta es donde está mi oficina, que era la antigua oficina de Fritz Haber. Y este edificio y otro que me están construyendo aquí son los edificios donde yo hago mi investigación. En la Sociedad Max Planck es conocido que nos dan financiación estable sin tener que tener proyectos desde que nos contratan hasta la jubilación. Y he puesto esta foto aquí porque Luis me comentó que la invitación, de hecho me la dio Luis, pero vino después de que viese la última visita que tuvo el rey a Alemania, que vino a visitar nuestro instituto, se interesaba por temas de catálisis y de hidrógeno verde. Entonces, agradezco a Luis y también la publicidad que me dio, que me permite estar aquí con vosotros. El instituto, para que os hagáis una idea de la historia, se fundó en el 1911 por un Kaiser Wilhelm, y es un instituto de física química. Del 2011 al 2018 se hizo investigación en armas químicas. Esto, por supuesto, es algo que preocupa mucho con la historia, pero en aquella época Fritz Haber, que era un patriota, decidió intentar ayudar a Alemania en la Primera Guerra Mundial, cuando Francia empezó a desarrollar y emplear las armas químicas. En el 1919 le dieron el premio Nobel a Fritz Haber, pero no le dieron el premio Nobel por desarrollo de armas químicas, le dieron por la síntesis de amonia, que os hablaré un poquito más hoy de ello. En el 1933, Fritz Haber decidió irse de Alemania, porque fue cuando empezó el movimiento nacionalsocialista en Alemania, empezó el movimiento nazi, y él decidió primero sacar a todos sus empleados que eran de origen judío, y resignó y se fue cuando Hitler empezó a preparar lo que luego sería la Segunda Guerra Mundial. En el 1948, de Casa Wilhelm Society se cambió el nombre a la Max Planck Society, y luego tuvimos distintos directores en el instituto. Os voy a dar algún ejemplo. Por ejemplo, Max von Laue, todos los que trabajan en cristalografía lo conoceréis, fue premio Nobel y fue director en nuestro instituto. En el 86, en Ruska, todo el mundo que enseña imágenes de microscopía, fue el que inventó el primer microscopio eléctrico. Y en el 2007 fue nuestro último premio Nobel como director, Gerhard Ertel, por el entendimiento fundamental de los procesos de la síntesis de amoníaco. Y yo me uní al instituto en el 2017. Aquí veis una foto, este es Fritz Haber con Einstein. Einstein era un visitante en nuestro instituto a menudo. Von Laue, Gerisha, que era Gerisha, que era un electroquímico muy importante, y este es Ertel en sus años jóvenes. Y algo muy importante, Max Planck, la sociedad Max Planck lleva el nombre de Max Planck, que fue premio Nobel por el desarrollo de la teoría cuántica, y algo que siempre dijo fue "insight must precede application", que quiere decir que primero hay que entender antes de poder aplicar y hacer transferencia de tecnología. Y esa es en lo que nos basamos en la sociedad Max Planck, ciencia, entendimiento fundamental. So I'm going to switch now to English because I'm going to start my science talk. But I wanted to remind you that the challenges from the 19th century are also coming back to the 21st century. For example, ammonia synthesis. And that's how my institute started, and that's how also we are now moving in this direction. So something important, think about 1898. So Sir William Crookes was at the time president of the British Academy of Science. He said, "It is through the laboratory that starvation may ultimately be turned into plenty. It is the chemist, or chemical engineer or physicist, who must come to the rescue and step in and postpone the distant famine. Wheat preeminently demands nitrogen. Using current farming practices, we are drawing on the Earth's capital, the natural fixation, nitrogen fixation, and our drafts will not be honored perpetually." What was the time there at that time? So we were here, this is the world population, and he was at this time, and they were realizing that we have problems with fertilizers. At that time, if they wanted to have fertilizers, they would send a ship from Europe to Chile. They have earth in Chile in a lake that had a very high content of nitrogen, and they need to ship it back to Europe. So imagine how energy efficient this was and how much this could be used. So wheat, bread, was something that couldn't be produced in the amount that we needed with the world increasing population. So at that time, Fritz Haber started to work in the ammonia synthesis, and the idea was to combine hydrogen and nitrogen from the air and then make ammonia, and with ammonia they can make fertilizers. So that was the reason why they gave him the Nobel Prize, and in German they call this aus die Luft Brot machen. This means from the air they made bread. So now we are coming back to ammonia because we have a problem of an energy transition, and one of the possibilities of the minimizing or trying to address the energy transition is to develop new technologies, in this case on, for example, green hydrogen. So we know that we can take water and we can split it in oxygen and hydrogen. But people have been thinking this is now an idea of the last years, and to produce hydrogen. But if you know Julio Verne, And in 1870, he said, I believe water will be one day be used as fuel, as the hydrogen and oxygen that make it up, used separately or simultaneously, will furnish an inexhaustible source of heat and light of an intensity of which coal is not capable. So when people are thinking now we are discovering new things, this was Jules Verne. We already knew how to do electrolysis back then, but it was not a technology that was necessary. It was at the time they have coal. They thought coal is very efficient. We can burn it. We can get our energy through coal. And so people forgot about water electrolysis for many years, right? 1870, and this was found in a novel, right? Jules Verne was writing novels. So. And now this is how it looks like. This is an electrolyzer, one of the ones that are currently being employed. And just to give you some dimensions, you need about 10 tons of water. And I mean clean, so if you use salt water, you need to take the salt all out first. And you need, for example, 50 megawatt per hour of green electricity, for example, produced through solar or wind, to get 1 ton of hydrogen. And then you get 8 tons of oxygen, which we should try to use in a meaningful way. But this 1 ton of hydrogen is very hard to transport, has a low energy density, so people are thinking about how to do this in an efficient way. So one possibility is to transport it into something like ammonia. And if you can use ammonia directly, then great, then you already have a high-value product. If not, you have an infrastructure already, for example, to ship ammonia. But I wanted to show you this just to make sure that you realize how we went back. So we started in 1911 with Fritz Haber looking at the ammonia synthesis to make fertilizers to address the problem of the hunger and the increasing world population. And now we have an energy problem, and ammonia is one of the energy vectors that we might use for transporting hydrogen and storing it. So we closed the circle, and we have similar challenges now in the 21st century. So in my department, we are working on the conversion of small molecules, either with thermal catalysis or electrocatalysis. And today I'm going to be focusing on the conversion of carbon dioxide and conversion of water. And I will give you some examples that the same type of materials are used in thermal or in electrocatalysis. And however, the reaction mechanisms are going to be very different. If we have from the posters that I saw, we have in the audience many people with expertise in synthesis, and so in my department we also have different methods to synthesize very well-defined size and shape control nanostructures. And I wanted to put this because with many of these pictures you can get nice covers in journals, but this is the pre-catalyst structure. So this is what you synthesize, and the reality is that under reaction conditions your nanostructures, your catalysts are not going to look like this. And you need to be able to understand what is the pre-catalyst structure and to tune it to the best that you can. You need to understand what do you get after reaction, but if you want to know about the active state of a material, you need operando microscopy and spectroscopy under realistic reaction conditions. And I'm going to emphasize realistic reaction conditions. It's not possible for every experimental method to apply it under realistic reaction conditions, but if you can, you must, because otherwise you're going to have a lot of information about the state of a material that is not the active state. It will be just this pre-catalyst. And I like to put it also like this, so this is the elephant in the room, because if you only look with one experimental method, for example here, this person, then might think that this complex catalyst is something that it is not. For example, here they only see the trunk, they think this is a snake. If they only see the leg, they think this is a tree. If they see the tail, they think this is a rope. And only when you combine the insight from all of these persons with all of these different perspectives, you will get to see that this is just simply an elephant, right? But very complex. And our catalytic materials are as complex as this. So catalysts are dynamic, and I wanted to give you some illustration about how complicated things are, even when you start working with a model system. So think about a single crystal. This is a copper single crystal, and you're going to see here, what you see moving around, these are steps. So here in black, these are nickel particles. And this sample is exposed to oxygen at about 600 Celsius. And even the perfect surface that the theorists like to calculate, if you put the environment, it's not perfect anymore, and you see these dynamics here, the steps moving around. Of course, this influences the properties of this surface. So if you are working in theory, the transition that we need to make now is to forget about the static structures. So the structure that you are calculating is going to be changing, rearranging. There are going to be fluctuations. And these are going to be driven also by the environment. It could be a chemical potential. It could be a change in the temperature, change in gas pressure, and electrochemical conditions, the applied potential. Now, another example here, this is, by the way, these data here are acquired with a low-energy electron microscope, and we have a beamline from the Max Planck Society in Berlin, where we have something called this low-energy electron microscope, also at the beamline, so we can get microscopy and spectroscopy especially resolved. So I can go to different areas of the sample and take Nexus spectrum or XPS spectrum and tell you what is the local structure and what is the local composition of the material and oxidation state. Right now, we are developing also these methods to work under more realistic conditions. Normally, these measurements were done in vacuum or under low pressure, and you already see that even at this very low oxygen pressure, there is a lot of changes on the surface. But we have been developing together with a company this new version of the microscope that can work under near ambient pressure conditions. Again, I start very simple, and then I will increase the complexity during my talk. So this is a single crystal. This is ruthenium, and we are following the formation of water on this surface with dosing of hydrogen and oxygen. And the dark contrast here indicates when you have high oxygen coverage. You prepare the surface in vacuum. You have a atomically very nicely organized surface, but there are always defects. And these defects act also as nucleation sites for the formation of different phases. And so now you see a chemical reaction on a surface, and you see that this is not homogeneous everywhere, right? And that this is a very nice indication that there are special sites even on a single crystal surface. So I wanted to start with thermal catalysis because there were a lot of talks yesterday, also people interested in CO2 hydrogenation and the synthesis of methanol, so we have a lot of expertise here. So I don't need to go into a lot of detail, but we were interested in following the conversion of CO2 in thermal catalysis into methanol. And we know from the literature there are this combination of copper and zinc that is a very good combination. We also know that it's good to have steps, so defective structures of copper, and then zinc in close proximity to these structures. But there has been a lot of discussion about how much zinc do you really need? Because normally in the industrial catalyst, this works at high pressure, moderate temperature, but you need this mix of copper, zinc oxide, and alumina as a stabilizer also. And our idea was, do you need zinc oxide as the support, or can you just have a little bit of zinc close to copper? At the same time, we wanted to figure out what is the structure and the composition of this catalyst under realistic reaction conditions. And realistic reaction conditions is not vacuum, and even we have some measurements also near ambient pressure. This is millibar. Realistic reaction conditions is when you go to 40 bar, to 20 bar. And this I will show you that we were able to do these experiments. Then we can figure out if there is a pressure gap. So we start with a catalyst. So we use colloidal chemistry to synthesize well-defined size and shape control pre-catalysts. We can use the block of polymers to make reverse micelles. Then we can either deep coat them on a surface and then remove the ligands with an oxygen plasma, or we can put them impregnate them in the oxide nanocrystalline support, and then we remove the ligands either with oxygen and also with a plasma in these powders. The nice thing about this method is that you can control the particle size by changing the length of this polymeric head, and you can control the interparticle distance by changing the length of this tail. So you can make the same particle size, but one could be pure copper, and the other one could have copper and zinc inside this micellar reactor. And so we started looking at what happens with the composition of this catalyst under reaction conditions, and we started with what we could do with the spectroscopy, first with near ambient pressure XPS. So this is about 6 nanometers copper zinc particles on silica, and we start with about 75% copper, and then this is zinc. And now you go to different reaction environments. And you can see that when you go to the reaction conditions, then either in hydrogen and CO2 or hydrogen, CO2, CO, and we also added some of the things that we are producing, water, to test if there was any difference, you can see that zinc oxide goes to the surface. So you get zinc at the surface, is zinc oxide, and you see the copper going subsurface. So this is a surface-sensitive technique, and I bring this to your attention because if you want to understand these materials, you need a combination of subsurface or bulk-sensitive techniques to get more structural information, but you also need the surface-sensitive techniques because you want to know what is really at the surface of your material. We started with something like this, domains of zinc oxide mixed with copper oxide. But once you put it under reaction conditions, you get a shell of zinc oxide around the copper. Now we wanted to see, we have these very well-controlled nanoparticles, and we wanted to see now what is the role of the support. And we compare the cases, for example, where you have zinc only in close contact with copper as part of the nanoparticle. These are about 3 nanometer particles. And then we did the same with pure copper on the traditional zinc oxide alumina. In black is the methanol production activity, and you can see that these two samples have very similar production of methanol, even though the one that had copper zinc nanoparticles only had about 30% zinc in these micellar nanoparticles. So we didn't need to have the zinc as part of the oxide support. The selectivity is also very good. This is making methanol. And if you put the same nanoparticles, copper zinc, instead of on silica, on alumina, we see that it becomes much more active, but unfortunately, we start changing the selectivity. We start making the methyl ether. This is not surprising because this happens on the alumina side, but you can play with the ratio of how much methanol versus the methyl ether you are making by tuning the content of zinc in these copper zinc nanoparticles. And I will tell you a little bit more about this in a minute. And if you take the same particle size, but you don't have zinc, you see that there is much less active system. So from this type of studies, we could learn the support matters, but you don't need the zinc oxide as part of the support. You can just put it as part of the active component within the nanoparticles. At the same time, in the literature, there's always this discussion, what is the active catalyst? Is this metallic copper? Is this brass alloy? And to figure this out is very difficult if you have the standard commercial catalyst, because normally you have the zinc oxide as part of the support, then you use a XRD or you use XAFs or a bulk-sensitive technique, and you see how everything changes, but you don't get really the surface signal. So when you only have a small amount of zinc, even though if you use a bulk-sensitive technique, you get all the information about the species that are changing. So we went to the synchrotron with this type of catalyst, and we wanted to, again, do the reaction at high pressure. We did 20 bar, 40 bar, and 60 bar in the real reaction mixture that contains CO2, CO, and hydrogen. And we had a mass spectrometer to see that we were making methanol. And we followed the copper signal of these mono and bimetallic particles on the different supports. And you can see that when you start the reaction, on all the supports, very quickly you see almost complete reduction. In the copper, because the particle size that we had was about, in this case, 3 nanometers, even though we see that this is metallic, I cannot exclude that there is not a little bit of oxygen still dissolving the copper. That is very commonly happening. But it looks mainly metallic. Now, if you look at the zinc data, this is very interesting, because now we can follow the zinc, because it's not part of the bulk support, and we can follow the transformation. And so if you look at the data on blue, this is the copper zinc particles on silica. And you see these two peaks here, and you see that it looks very different from any normal zinc oxide structure that you could find. So the zinc in these nanoparticles, the zinc oxide is highly disordered. But if you compare with the same particle size and the same composition on alumina, this third peak appears here. And when you look at the reference, you realize that this indicates the incorporation of zinc into the alumina. So you make this spinel, this zinc alumina spinel, and this is actually the catalyst under reaction conditions when you have alumina support. So with alumina, you start with something like this, and then unfortunately you lose all the zinc. It goes and becomes incorporated into the alumina, and you end up with a mainly metallic particle. This is the catalyst that I was showing you before that makes a mixture of methanol and methyl ether. And the question in the literature, are we making brass, and what is the implication of that? Now, because we can follow the zinc signal in high detail, we can see we are making brass. These are Fourier transform X-ray absorption spectroscopy data, EXAs, and we look at different temperatures, and if you stay at the low temperature for about 24 hours, we make brass. If you go to higher temperature, you can see it much better. And this is the example. This is here zinc oxide. Now, this peak here corresponds to zinc-oxygen bonds, and this corresponds to zinc-metal bonds. And under reaction conditions, these shoulders start showing up here. So yes, you are making brass. And yesterday was a debate whether this is the active catalyst or not. And brass makes also methanol, but not as good as when you have copper in contact with zinc oxide. So we learned from this data with the X-ray photoelectron spectroscopy, we learned that we have the zinc oxide cell, but then under reaction conditions, over time, you see the formation of a brass phase also. So you have a mix. It's not all brass, it's not all metallic. There is a mix of brass, metallic copper, and this zinc oxide cell. And if you look at the performance of this catalyst over about, in this case, 250 hours, you can see that the copper zinc catalyst on silica that started to make the brass initially is very active, and then after about 50, 60 hours, when you start making significant amount of brass, this starts to deactivate, and then it goes to this steady state. And when you have the same catalyst on alumina, where we didn't have the brass formation, where all the zinc became incorporated into the alumina, you see that the activity it goes up, you activate your catalyst, and then it stays stable. The only difference is that on the alumina, you also make the dimethyl ether. So with this, I wanted to illustrate that we have already all the tools now. These measurements are done at a synchrotron, but this is accessible for everybody. You have a great synchrotron with these capabilities also here in Spain, ALBA. And you can follow each component of the material under realistic reaction conditions now, so under the industrial conditions of 20 to 60 bar. Now, going back to what are the parameters that affect the performance of copper zinc catalyst. So we thought in the previous chapter, I was showing you the role of the support and how much zinc we needed. Now I wanted to see what happens if we start with a particular structure, a shape, because theories are calculating for many years different orientations of copper. They say 111 versus 100. One is more active than the other, and experimentally, we wanted to work with a system that will be more realistic, so we want to work with a nanoparticle. And we started with these copper oxide nanocubes, and we wanted to compare the performance of this with something of the same size, but with this spherical shape. So we can make these copper oxide nanocubes. You see here copper is in red and zinc is in green. And then you put it in hydrogen at 170 Celsius for I think this was about 12 hours, and the shape of these copper oxide cubes was still there. If you go higher in the temperature, you start seeing the changes. But at least at this temperature, we can still have the copper oxide cubes with the right shape. But now we go to the same temperature, and we put the reaction conditions, and you see already the changes. So here I make this larger. You see the copper here. You are losing this nice, perfect cubic shape. You start to become rounded. But if you start with this pre-catalyst shape, you already ensure that you have a large surface contact area with the support. I think this is very smart for this system because the system likes to encapsulate the copper. So if you make something like this, maybe you get higher active interfacial area. So that was our hypothesis, even though we knew that the shape will be having changes. So we can follow this. We have, again, X-ray absorption spectroscopy under reaction conditions, and 1 bar and 20 bar. And you can see that this is the copper-copper signal, and this is the initial nanoparticles have metallic copper and the copper-oxygen bonds. Then we start going to the reaction conditions, about 250 Celsius, 20 bar, and this peak starts increasing, so you see more metallic copper. But this doesn't get completely reduced, and this is the copper-oxygen bond. So when you start with this copper oxide precatalyst, some oxygen is retained in the material. And we believe this is good, because this also helps us to minimize the brass formation, which is actually leading to the activation. We can also follow these different species, and you can see here under reaction conditions, the signal of copper 2O was decreasing, and then you never go to completely zero. You keep between 1% and 7% of this oxygen in these structures. So now we'll look at the reactivity. Again, I compared 3 samples. I have the commercial catalyst that we bought. This is alpha Esser. Then we have copper spheres, same size, and then we have our oxide cubes. And if you look at the methanol yield, the cubes at all pressures and all temperatures that we investigated, they are always performing better. So they are more active than the same size spherical particles and than the commercial catalyst. And we can also follow with our spectroscopy and microscopy data what is the performance of these materials. So if you start with your precatalyst, looks like this. This is how it will be at low temperature. Once we start the reaction, it starts to reshape. You get something more like this. And then I will demonstrate in a minute that under reaction conditions, you get an overlay of zinc oxide. And if you go, and this is still very good performance and stable. But if you go higher in temperature, in this case 280 Celsius, you start seeing the deactivation. And this deactivation we can spectroscopically assign to the formation of brass. So keep in mind that there was a lot of discussion also if the deactivation was due to sintering. Here, in these particles, we see both sintering and the formation of brass. But in the small micellar particles that I could put farther away apart from each other, there was no sintering after the reaction. And still, I saw the deactivation when I was making the brass. So I show you some of the bulk-sensitive techniques, but I wanted to bring also, copper is a very good material to do a spectroscopy with Raman, because it has a very good surface-enhanced Raman signal. So in this case, we develop a Raman cell that can work under 15 bar, so we can get closer to the reaction conditions. And we look at these samples, the cubes and the spherical precatalyst, under reaction conditions, and we start monitoring the formation of formate. These are the formate bands. And we get from these Raman shifts certain values, and we're looking and talking to the theorists and telling them what does this correspond to. So Felix Stud in KIT in Germany calculated the Raman frequencies of formate on different facets of copper, on the copper zinc alloy, and on zinc oxide, on copper 111 and on copper 100. And you can see that the changes are very large. We are not talking about very small differences. And the values that we are getting, both for the cube precatalyst and also for the spherical precatalyst, these fit very nicely with a zinc oxide overlayer on copper. But there is a difference when you have mainly 100 versus 111. Here, in theory, it's about 10 wave numbers. Experimentally, we see a small difference. It's about 4.4 wave numbers. But this is no wonder. I show you that my catalysts don't stay as cubic perfect. You see this rounding, but still we have a preferential texturing of the 100, even when we run the reaction over extended periods of time. So with this, we could show, yeah, on the surface, under reaction conditions, you have the zinc oxide. And actually, having this initial precatalyst structure that evolved under reaction conditions help us to maximize the contact with the active interface with the zinc oxide. Maybe it facilitates also this overcoating. And you can see here that you can distinguish this. I'm showing here format, and I always get the question, do you know if format is the intermediate? No. I know that I can detect it. This could be a spectator. Maybe it's methoxy that is converting very fast what is really the intermediate. But experimentally, normally, you get to see the most stable species, and I can detect that under reaction conditions, format is on the surface. If this is the intermediate or if this goes to methoxy very quickly, I cannot tell you that. But at least we need this information, what you have on the surface under reaction conditions, to get an idea. For example, what will be the surface termination. So from this first part of my talk, I hope that I could illustrate how even very well-defined precatalysts are modified under reaction conditions, how the structure and the compositions affect the activity and the selectivity. I talk about the brass formation, and I talk about the increase in this interface between the copper and the zinc oxide, how the support matters, the shape of the precatalyst also matters, even though it's not a traditional shape effect, it's just the shape changes, but it tunes the contact area with the active component. So I know that some of you are very interested also in electrochemistry, and I started in thermal catalysis, and I decided to make an excursion into the liquid medium and into electrocatalysis. And the same type of catalysts are actually very good for converting CO2 electrochemically into something useful. So we want to use green electricity to go from CO2 into hydrocarbons. In this case, you have ethylene, for example, or into fuels like ethanol. And this is possible, but it's potential dependent. And to get these interesting products, you need to go to very high overpotentials. But for a fundamental point of view of research, this is a very interesting problem, because anything that you do to the structure of your catalyst, the size, the shape, the defects, if you have subsurface oxygen, and even the interaction with electrolyte, all of this is going to affect your selectivity. So it's a perfect playground for the students that want to do catalyst design and see if this has any influence in the performance. So I use this to illustrate a couple of points that I think are very important and sometimes are forgotten. The active sites are not static and might be created during activation. Most of the time are created, in fact, during activation, during pretreatment, and during electrocatalysis. So you see here a single crystal. Again, I start from simple, And I will show you how difficult it is already to start to even understand a single crystal. So there were discussion in the literature, and there were predictions from different theorists saying that if you have 100 versus copper 111, you get different product selectivity, with ethylene being produced on 100 and more methane and other products on 111. And a theorist calculates the perfect surface. So we thought we make a surface prepared in UHV, so ultra-high vacuum, with very large terraces, very well-defined steps. And then we do the reaction, and you can see that under reaction conditions, again, electrochemical conditions, apply potential. This is potassium bicarbonate electrolyte. And you see that the steps are still there, but the surface becomes very rough. So this is not considered by any of the theoretical calculations. But even worse, when we look at this surface here only makes hydrogen. This is the parasitic reaction. We wanted to go from CO2 to hydrocarbons and alcohols, C2 plus products, and we end up making the perfect surface, and we only make hydrogen and a little bit of formate. Only when you mistreat this surface, only when you create defects, for example, doing an electropolising treatment, you get this type of structures, that starts to make hydrocarbons. This is before reaction, this is after reaction. So all the theories were comparing to electrochemical data produced after electropolising, but they were assuming that the surface looked like that. And what we learn is with simple experiments, just CO is one of the common intermediates here. So if you dose CO on this surface, or on this surface of the precatalyst, on this one binds stronger. So you can see the CO-TPD here on the electropolis sample, and you see that there is a shift in the desorption temperature of CO from this surface, higher binding, stronger binding, to this one, weaker binding. And we can go further, and we say, okay, we can prepare surfaces with different degree of defects. So we go here from the perfect UHV surface to a surface where I take an argon gang and I create defects, a surface where I do electropolising, or a plasma surface, treated surface. So this is with oxygen plasma, so very, very defective. And then we look at the activity. Here I'm showing you, in an electrochemical activity, I'm showing you current density. And you can normalize it by the surface area, or you can do the more meaningful normalization that will be the electrochemically active surface area. And interestingly, the higher the roughness, we saw the decrease in the total activity. This is counterintuitively, because we were thinking we are making defects and we see less activity. The question is for what? So you can separate the different products. You can separate the current that is going to making hydrogen. And this is our parasitic reaction. And this is the one that is decreasing when I enhance the roughness. So this sorted a lot of discrepancies in the literature, because by working with these single crystals, we could figure out the surface is flat, highly coordinated copper atoms, but catalyst, this makes hydrogen. If you start creating the defects, you see here the other CO2 electroreduction products, they are not changing drastically when you change these treatments. That means that there are different active sites for making hydrogen and for making CO2. Once you know this, then you can try to design your catalyst that in a way that have these right defects that don't make hydrogen. So these are normally step surfaces, and we know now a little bit more, and you will see it during my talk. So the second take-home messages for the student will be that the catalytic surface is restructured under operation. So unfortunately, we didn't start with a single crystal work. We started with something like this, because the theorists were telling us, make 100 surfaces, and you will make ethylene. So we made them. We made these cubes. And then we saw, yeah, we make ethylene, but this doesn't stay like this. And that's when we started to wonder, okay, let's go back, look at a single crystal, and see what happens there. But just to show you what happened, so we have images in a transmission electron microscope. These are a video of a catalyst. This is copper oxide cubes during CO2 electroreduction. This is when we start. And you see the mobility of the nanostructures. You see that they break up. You see the dendrites forming. Tell me that there is no chemical dynamics here. So this is not pure dynamics, because I'm changing the applied potential, right? So this is at constant applied potential, but it's not just fluctuations without applying a chemical potential. But this is certainly a catalyst that is restructured under reaction conditions. You see formation of small particles. You see the dendrites there. And this restructuring, of course, depends on the support. Now we have the capabilities to do this in the liquid phase, right? So it's hard enough to do before and after transmission electron microscopy images. It's very hard to do it in the gas phase. This was heroic work of my group leader, because imaging in the liquid and also trying to avoid artifacts, which we do very carefully, is very challenging. I want to show you also that if you put, for example, the same nanostructures on a carbon support, and you do also the reaction, you start seeing the formation of this porosity, because under reaction conditions, these copper oxide cubes are going to start reducing. Pieces break up, and you see them here. They dissolve, they redeposit on the sample. You see things moving around, right? So this is a real catalyst at work. And to get understanding about this catalyst, I can get the cover of a journal showing you my perfect copper oxide cubes, and I can say this makes a lot of ethylene, it's true. But this is not the picture. This is the picture. This is the real catalyst. And so we came up with this idea that we start like this. We start having the reduction of the copper oxide cubes. We see these small particles that are forming. And then at some point, you end up with something like this, a porous catalyst with a bunch of small particles around. So theorists don't like normally to see this because it's very complex, but you can try to decompose the problem into what are these guys doing, what are these guys doing, and then try to put it together. And if the images are only showing you that the catalysts are changing, but if this doesn't show you that this affects the activity or the selectivity, then it shouldn't matter for catalysis, right? But I want to illustrate that it matters. So we started with two different cubic precatalysts, about 170 nanometers and 80 nanometers. We can synthesize them electrochemically. So we synthesize them applying potential pulses. They are very stable. We can synthesize them on the same TM chip where we are doing the in situ measurements. And now, just putting them in the electrolyte, you can see this sample, just putting them in the electrolyte already saw drastic transformations. Here, the same thing. You start having desorption of some of the cubes. But now I'm going to apply the potential and start doing CO2 electroreduction, and you're going to see, again, how is the restructuring of all of both of these samples. So in the top image, you see these small particles. They are growing. They are moving around. On the bottom image, you're going to see here the formation of some chains. So this catalyst looks like dancing particles. They move around. They make these chains. So this is reality. I started like this. The material likes to make that. And here you even see a depletion zone around the large particles. So there is a lot of restructuring here, but around the particles there is no material, which I also think is very interesting. Another thing that you need to watch out if you are publishing this type of data, you want to publish the selectivity, and most people in the literature with CO2 electroreduction, they show you, these are my data after 1 reaction hour. If I show you the data after 1 reaction hour, this sample and this sample perform very similar. This is ethylene, what I wanted to make. This one here is much more stable over time. This is just 12 hours, but you already see the deactivation, but more stable. But this one here, after the 1 hour that was stable, boom. So you stop making CC products and start making CO. So with this, I hope that I could show you that it's very important to do the in situ characterization. And now, something that most of the time we try to explain the data with things that we can easily detect. But in most catalysts, the reaction intermediates of the minority species are really key. And these are the very hard ones to see. So for the ammonia synthesis catalyst that I mentioned at the beginning, it's not iron, the active catalyst. It's iron with all the dirt that were what we call now promoters. So you can call it minority species, you can call it promoters, but we need to know if this is in the material. And in CO2 electroreduction, people knew that if you start with a copper oxide precatalyst, and the reaction conditions is reduced. They were looking at this with bulk-sensitive techniques, and was more active. But people were saying it's metallic, and it's just rough, because when you reduce the oxide, you get more low-coordinated sites. But we were thinking maybe there is also some oxygen there, because in the thermal catalysis, we know that it's almost impossible to get copper without oxygen. And so why not here in this aqueous environment? So we went to the synchrotron, and we developed the operando photoemission measurements for this type of catalyst under reaction conditions, so under applied potential. So you have a cation exchange membrane. You have here the liquid. You have your copper oxide cubes deposit here, and then you seal it with a graphene membrane. This allows you to have a transparent membrane where you can do photoemission. These measurements were done also at the synchrotron in Berlin. And you can measure all the electron yield, and you can see that when you start at the positive potentials, you see from the references, copper, I told you, is very good for Raman. It's almost good for everything because it has very specific spectroscopic signatures to distinguish copper O, copper 2O from metallic copper. And you can see here that at the high applied potential, when you're in the oxidizing regime, you see copper 1 species very well and copper 2. Now you start reducing, and you can see here, this is the copper 2 is gone, and they still have copper plus. But if you go to the reaction conditions, this here, the ratio between these two peaks and the shape doesn't look like metallic copper. So you don't need to be a spectroscopist to see that this ratio here and this shape is not the same. So we could show under reaction conditions that you have some oxygen dissolved in this material. And every time that we see this, we are able to get oxygenates out of this material. So we can do CC coupling efficiently, and we can go into making, for example, ethanol. So I mentioned before trying to see what you have on the surface, so we want to learn about intermediates, and again, we can go back to surface-enhanced Raman, and then follow the signal of these samples and apply potential control, and see what do I have. And the first intermediate that you can monitor is CO. So you can look with Raman signal, the binding of CO on the copper surface, and you can see that with increasing potential, here's where we are doing CO2 electroreduction to the interesting products, you see that there are two possible binding configurations. This is this stretching vibration, and this is the frustrated rotation vibration. And the ratio between these two features, actually working with a theorist in Spain, Nuria López in ICIQ in Tarragona, she showed us that the ratio between these two features is related to the CO coverage. So the highest the ratio between these two vibrational configurations of CO, the higher the CO coverage on the surface. And very interestingly, if you look at the production of hydrocarbons, in this case mainly ethylene and also alcohol, ethanol, versus the applied potential, there is a maximum here around minus 1.1 volt. And if you look at the ratio between these two features, that indicates the maximum CO coverage, there is also a maximum around the same time. So it seems that you need a high CO coverage on the surface to favor the CC coupling and to go to this production of hydrocarbons and alcohols. So this looks nice, but if you're talking to the theorists, they show you many different reaction pathways, and they tell us, yeah, theoretically, sometimes going to ethylene versus ethanol energetically is very similar. Tell us what are possible intermediates that you can detect on the surface. And CO is at the very beginning, and we want to go to ethanol. So it would be nice to be able to see some other intermediates. So we spend a lot of time trying to develop very rough surfaces and very active, where we can have a very large surface-enhanced Raman signal. And then maybe we can see not only CO, but also some other intermediates. And we managed to do that very recently, so this is still unpublished. So this is the production of C2 plus products. Here is ethanol that starts a little bit later than the production of ethylene. And if you look at the Raman data, at the different applied potentials, here is when we start making ethylene, here is when we start making ethanol. There are clear differences, again, you can see this by eye, in the spectra. So we could see that we can detect, first of all, not only CO, but now we see other vibrational features. And working again with Nuria López and her postdoc or student Federico Dattila, we could see that at the onset of ethylene, there are these intermediates, and at the onset of ethanol, there are these other intermediates. And like this, we can propose a model. It seems that there is a common intermediate, but then depending on what you have on the surface, you can go to ethylene or to ethanol. So working with Nuria, we also learned that the CO binding, the CO Raman shift is different when you are absorbing CO on differently coordinated copper. I show you that my surfaces are very complex. My surfaces don't have only bulk coordinated atoms. Normally, under reaction conditions, you even see the formation of clusters on the surface. We have microscopy data for that. That means even on a single crystal, you create clusters and low coordinated sites under reaction conditions. And this affects the coordination number of copper that normally should be 12, could be 7 to 8, could be smaller, and this causes a very large Raman shift. So this is very nice because we can associate this to what we are seeing in our experiments. So if you look at this Raman shift frequency range with SERS, here is where we are making ethanol. You can see by eye, this feature shows up here very prominently. Here's where we start making ethanol. It looks different. So you can try to deconvolute this data, working with the theorists, again, assigning different Raman frequencies to different fragments or intermediates. And we learn that if you have high coordinated atoms on the surface, same as we saw in the single crystals, then you make hydrogen. On the sites that have lower coordination, you can make ethylene or ethanol. And for the calculations, it seems that when we have the lowest coordination and the better, if there is some oxygen around, then you favor the production of ethanol. And this intermediate coordination helps us the CC coupling to make ethylene. And this is also made on metallic sides. So you can propose a model like this. Experimentally, now we don't only detect CO, we can detect this here, this intermediate, we can detect this here. And looking at the bond lengths, we can even infer whether we are going this way, again, or we are going this way. And this depends on the structure of the surface. And not on the initial structure, but on the structure that form under reaction conditions. And we make both at the same time, so it's not one or the other. It's different sides will be making this preferentially or this. So I wanted to show you that we start step by step trying to understand which parameters are affecting the catalytic performance of our material. And then we realize, okay, it's good to have maybe defective structures. We want to understand which ones, right? Because not every defect is the same. It could be a step, and then you talk to a theorist and say, which step? I want the orientation. And things get more difficult. Then we say, having oxygen there is good. But if you're working on that very negative applied potential, very easily you can reduce, even if you don't reduce completely. So we try to force the system. So we try to say, we are going to be applying a potential, and we are going to be able to pulse. And by going to anodic potentials where we oxidize the copper, we are going to try to have a mix of metallic copper and copper plus species. This is here the potential where we're doing CO2 electroreduction. And this is here where we are having this mix of metallic copper, copper oxide. So very simple. You just use dynamic reaction conditions. And when we do this, we wanted first to see, does this applied potential pulses restructure the surface, not just change the oxidation state? Again, we have our synchrotron beamline here, and we can do microscopy and spectroscopy simultaneously. This is a copper 100 surface, again, very flat single crystal. And you do CO2 electroreduction for about 15 minutes. The surface looks flat. Unfortunately, here we do quasi in situ. We have the electrochemical cell attached to the microscope, and we transfer without air exposure. But with this NAP, near ambient pressure, LIMEX beam that we just purchase and we are adapting for electrochemically, hopefully next year we're going to be able to do it also under reaction conditions. This is a prototype that doesn't exist anywhere else. So if you go now to the potential applied pulses and you go to the oxidative regime, this surface looks much rougher, and then you start seeing these things. So now I can go to my theorist colleague and I can tell them, okay, the defects that I'm forming and that are very good for making ethylene have this structure. They are N10 steps. Isn't it nice, right? Now I can tell them, start with this. It's not 100. This makes hydrogen. It's these structures that I'm creating here, which does the CC coupling. And now I can go also locally and do spectroscopic measurements. So I can do my Nexus measurements, and I can see here, if I stop at the positive applied potential, I don't have metallic copper. And if I go to the negative potential, I see the strong reduction, but look at this data here. Always we are trying to explain catalysis based on shifting the D-band level. But what about P and D states? These also play a role. And we can see that things are changing. Right? So if you are working in theory, think a little bit about not just looking at the D state, but look at the others that might also have an important role. In any case, what we could prove is that there is defects created during these pulses, and that there is also a copper-1 species or subsurface oxygen there under reaction conditions. Then we decided to tune this. Now I have the pulses that I can control whether I'm oxidizing or not, but I can also change the length of the oxidizing pulse versus the pulse where I'm doing CO2 electroreduction. Same catalyst as always, these copper oxide cubes. And as electrochemists, we could make this diagram. Ethanol production, ethylene, CO, methane. The change in the color is how much more in red or how much less in blue we are making with respect to when we apply and run these catalysts under potentiostatic conditions, only at constant -1 volt. If you do it at constant -1 volt, ethanol, this is in white, there is no difference. If you start applying these potential pulses and you get more ethanol, then you see it in red. If you get less, you get it in blue. So these diagrams show you here that there is a particular length of the anodic pulse and the cathodic pulse where making a lot of ethanol. So this is nice, and now I say, okay, how do I tune this catalyst? I know now, I apply the potential pulses, I get to the hardest product to get from CO2 to ethanol, but what is the structure of my material? So now there is possibility of combining different methods at the same time, and again, synchrotron measurements. These were done in Switzerland, and combining X-ray absorption spectroscopy, which gives us information about the local structure, ordered and disordered phases, and also X-ray diffraction, which gives us information about the crystalline structures. And we have the possibility of doing quick measurements. Quick means sub-second resolution, even millisecond resolution. And I can follow during these potential pulses how the activity changes. This is the current here. But I can see how the material oxidizes, copper 1 species, copper 2 plus species. Oxidation is slow during the applied pulse. Okay, it's not good. It's back, okay. Sorry. So the oxidation is slow, and the reduction is very fast. But many times people are trying to make conclusions about only XRD data. With the XRD data, I can follow the crystalline phases. For example, these are the XRD data of the metallic copper component and also of the copper 2O that I have under reaction conditions. But once I see it in XRD, it's bulk-like. Here, XRD gives us everything, also the local order, the highly disordered phases. And in catalysis, many times it's these amorphous, highly disordered phases that actually the active phases. And I wanted to show you that, for example, if you look at in XRD at the crystalline phases, we can look during a pulse at the strain that I have on my material. So catalysis and being able to tune and to artificially force your material to look like something else, for example, strain it, you can do this by applying potential pulses. And you can follow also this along different directions. But the beauty of this combination is that it gives us a holistic view of what my material is doing. I know the structure from microscopy. Now with the spectroscopy, I can tell you what is happening here and correlate this to the selectivity. So if I have a mainly metallic catalyst, which is not perfect, so it's not a perfect cubic structure, it's a defective structure with these N10 steps, then this is very good for making ethylene. If in the region where I'm making ethanol, I don't have metallic copper, I have metallic copper in close contact with copper 1 and copper 2 islands, highly disordered, XRD invisible, only X-rays visible. And if you start growing a very thick oxide layer, this is here the length of the cathodic pulse. This is here the length of the anodic pulse, the different regimes I showed you before. If you start growing a very thick oxide layer, for example, long anodic pulses, you start making only C1 products, CO and methane. So now I can say, okay, I can design my material. I want these steps. I want the combination if I can leave some of this oxygen there. I know what to do with my material with this highly disordered copper 1 and copper 2 species. If you are a synthetic chemist, try to make this. If you make this, then you are going to get a catalyst that will make ethanol. And make it and try to get it stable under reaction conditions. So I wanted to show you now that I started with CO2 hydrogenation in the gas phase, and I wanted to show you that exactly the same material, zinc oxide and copper, also do CO2 electrochemical reduction. And the same questions that we are discussing, are we making alloys? Does this affect the reactivity? Are appearing here. We have different intermediates, because in CO2 hydrogenation, the product is methanol. In CO2 electroreduction, under the different environmental conditions, we don't get formate or methoxyous intermediates. We go directly to ethanol production. We don't make methanol at all. So same catalyst, but different selectivity on the different environment. So we created these copper oxide nanocubes, and then we have this zinc on the surface. And you can see here that the Faradaic efficiency versus time depends on the amount of zinc that you have in these copper zinc structures. If you have only a little bit of zinc, you get very nice Faradaic efficiency for ethylene, which we wanted to make, and it's stable. But if you start putting too much, you see this deactivation. So you can follow this now under reaction conditions with X-ray absorption spectroscopy. You can follow the zinc signal, and you can see that you are forming copper-zinc brass alloy under reaction conditions. And the realistic catalyst has a combination of zinc and this copper-zinc, and also some zinc oxide. I wanted to illustrate that we can do this very carefully. So we can use neural networks and train these neural networks with theoretical structural models to fit our X-ray spectra, and we can get radial distribution functions. So for this complex material, to find out sometimes minority phases, you cannot just do a simple linear combination analysis. This is the first analysis, but you need to go into this to really separate these phases. And we can do this beautifully as a function of time. So this is here the reaction time, and I can separate what will be the zinc oxide, I can separate what are the FCC-like alloy and non-FCC. And this is here as I'm running the reaction, when I'm seeing the deactivation of this catalyst, making less ethylene. And when we are making less ethylene, we are increasing this FCC copper zinc alloy, so we're making brass. And you see that you are decreasing this phase that will be the zinc oxide. So you can see that initially you have this order zinc oxide. After reduction, you make this copper zinc alloy that is FCC-like, and you also see non-FCC phases, zinc. But this here, the formation of this, is responsible for our deactivation. So to wrap this up, I hope that I could show you that these catalysts are restructuring, they are changing again in composition. You can tune this by applying potential pulses, and give you an idea that thermal catalysts and electrochemistry have a lot of things in common. We have a different activation way, so we don't heat, we are using an electrical potential, but the catalysts for CO2 conversion are the same. The problematic of having metallic copper or copper plus or having brass is the same, but you go through different intermediates tuned by this environment. I'm assuming that I'm completely out of time, so I'm going to skip the last part. This is what I'm splitting. If you have interest, I will tell you in the coffee break, and I will wrap up. So the take-home messages of my talk are that the asynthesized materials are pre-catalysts, and they react and adapt to the reaction environment. The pre-catalyst structure, however, influences the adaptability and the subsequent operando transformation. So if you are a synthetic chemist, it's not everything is lost. If you are able to tune the pre-catalyst structure, you are going to influence how this performance is going to change. But the reality is that knowing everything about this is not going to tell you what are the active phases. The active state of the catalyst is formed during the catalysis. That means that if you want to get mechanistic understanding, you can only get it if you characterize under realistic reaction conditions. And realistic reaction conditions is not millibar. For many of the methods, we cannot go higher. But for some of these reactions that happen at high pressure, we really need to work very hard to do measurements at high pressure. Trace amounts of non-metals in metallic catalysts tune the local structure of the active sites in morphology and electronic structure. This could be oxygen, this could be carbon incorporated into the material. We could get things from the electrolyte, for example, iodine that we are using in these electrolytes. All of these are going to be part of your catalyst and are going to influence your performance. The active states are in between formal oxidation states. In many cases in catalysis, you think that what you need is not the most stable material. What is doing the catalysis is what we call the frustrated phase transition. We start with a pre-catalyst, and we want something that doesn't convert completely to the most thermodynamical state, because that will be the dead, deactivated state. So frustrated phase transitions, in this case, in between formal oxidation states. I show you from some of our data that it's not only the states that matter, but SMP states will also affect the intermediate binding. And finally, Albert Einstein, who was a frequent visitor of our institute, the Friedrich Institute, said, everything should be made as simple as possible, but not simpler. So this means that catalysis is very complex. I show you single crystals that are very complex. Industrial catalysis is much more complex than anything that I show you here. But having this insight and trying to apply it, including method development, to more complex systems is what we need to do in this community. And I think we are making good progress on that. So I'm enjoying Torremolinos here and the very nice people that have been hosting me here since I arrived, but these are the people that did the work. So these are my students, postdocs, and collaborators in different synchrotron facilities, and I'm very happy to have this team. And I started here looking at the excellence that we have in Spain in terms of junior scientists, senior scientists, and also postdocs and students. And if you want, we have a couple of people from Spain here, but if any of you are interested in doing postdoc or PhD studies or even research stays, contact me. I will be very happy to host you. And thank you.
Bueno, no sé si se escucha. ¿Sí? ¿Tenemos tiempo para alguna pregunta o comentario breve? Muchas gracias, Beatriz, por la presentación. ¿Alguien quiere hacer algún comentario o pregunta?
Thanks for the presentation, it was very nice. I'm just curious because all the time we are talking about pressure, but what about flow? Because flow also have very strong limitations later with the mass transfer, can completely dramatically change the selectivity, and of course the molecules that will be around the catalyst. So I wonder if you have think about that.
Yes. So, of course, first we optimize our reaction conditions, and in thermal catalysis the flow is very important, but in electrochemistry it's equally important. We have done some of these experiments also in gas diffusion cells, where you can also control this. And yes, if you have mass transfer limitations, you change the selectivity. You also have local gradients in the concentration of the reactants and the products, and this also changes the local pH, and the local pH affects the selectivity. So it's a very good point. We are looking at this, we are aware of this, and the reactor design is key, not just in thermal catalysis, but also in electrochemistry, as I mentioned, for example, in these gas diffusion cells.
Bueno, pues como va a estar hasta mañana con nosotros, si hay alguna cosilla más en el coffee break o durante estos días, se lo comentamos. Le vamos a dar un fuerte aplauso y un regalillo que tenemos para él.